Hello and welcome to this short little series of videos on Equilibria. So what we're going to be looking at in this video in particular is we're going to be talking about where Equilibria sort of arises and talk a little bit about reversible reactions. We're also going to talk about what a closed system is, what an open system is, and then we're also going to talk about what dynamic equilibria actually is. Okay, so first off, let's talk about where equilibrium comes in. Okay, you would have done loads of different reactions and probably written out many reactions where you have a symbol in the center of your reaction between the product and the reactants that looks like an arrow. Now, this arrow means gives. Okay, so if you have the reactants, they will give the products. Now, a reversible reaction is when the products can also make the reactants. And we illustrate this ever so slightly different. So we have the reactants here, we have the products here, we have a different arrow that we use to illustrate a reversible reaction. And it looks a little bit like that. Now, a very standard question for equilibria is what is the symbol used to denote a reversible reaction? And this symbol right here is the answer to that question. Okay, fantastic. So we have a reaction that can go in both the forward and reverse directions. Now, what is this closed system and what on earth does it have to do with equilibria? Well, before I describe what dynamic equilibrium is, we need to talk about what a closed system is, because dynamic equilibrium can only occur in a closed system. I want you to imagine a box. Okay? We have a box, and this box has a lid. Okay? Now, inside this box, we have a reaction occurring. Okay, we have some reactants, which I'm going to have as blue, and then we have some products being produced, which I'm going to have as red. Okay, now if I was to have a box like so, but this box is slightly different in that it has an open lid, what could happen is I'll have my reactants and my products, but then what these products could do is they could leave said box, as could my reactants if they wanted to. This is the difference between a closed system and an open system. This system is known as closed. This system is known as open. So a closed system is where there is no loss of reactants or the products. Conversely, an open system is where maybe gases could escape. As an example. Okay, so this concept of dynamic equilibrium only happens in these closed systems here, okay, where our products and our reactants cannot be lost. Okay, so if we've got this closed system, we've got this box, and we put some reactants in it. So I'm going to draw a little graph. Looks a little bit like so. Okay, now on this side, what I'm going to have is I'm going to have a percentage, and my percentage goes from 0 to 100. And down here, I'm going to have time. So I've already used blue and red as my products and reactants, so I'm going to use those again. My reactants as blue are going to start at 100%. My products as red, they're going to start at 0%. So what's going to happen over time is our reactants are going to react together and they are going to then level out. Okay? Our products are going to do the same. So what they're going to do is there's going to be none of them to start with, but over time they're going to increase. And then they're going to level off. Now, at this point here, where both our products and reactants are constant, then we've reached what we call dynamic equilibrium. Now, notice that dynamic equilibrium, or equilibrium, does not mean a 50-50 split. Okay, that's not what dynamic equilibrium means at all. Okay, what dynamic equilibrium means is it means that the forward and reverse reactions are happening at the same rate. So, what that means is it means the rate at which the products are being made is the same rate at which the reactants are being reformed from the products. Okay, I've used a couple of words here. Forward and... Okay, so I've used a couple of words here. Forward and reverse reactions. Well, this is hopefully a little bit of common sense here. If I was to take this as my reactants go to my products, and this reaction is reversible. This direction, going from reactants to products, is my forward reaction. Going this way is my reverse, also sometimes called the backwards. Okay, so what we've got is we've got this concept of equilibria, okay, which only happens within a closed system. So a closed system is one where there's no loss of reactants or products. We've got this concept that what dynamic equilibrium is it's the point at which the forward and reverse reactions are occurring at the same rate. So it's not when we have this 50-50 balance. So to illustrate that, looking at this graph here, you can see that my products is somewhere at the 75% mark and my reactants are at the 25% mark, and they just stay at those levels. So we've got this key definition, okay, of what dynamic equilibrium is, okay, which is that it's when the forward and reverse reactions are happening at the same rate, and this can only occur in a closed system. So that concludes this little introduction into equilibria. What I'm going to talk about in the next video is I'm going to talk about the factors that affect what we call the position of equilibrium and how we as chemists can use that information to work out the conditions required for a reaction to give us the highest yield that's sort of profitable. Okay, so thank you very much for watching. I've been Sensei Science, and as always, I'll catch you in the next video.